Right, so today is the last lecture. Probably we'll have got through about a quarter of the topics that I wanted to cover, but most of all I want to get to this picture where we can get knots from all knots and links from the Thompson group and somehow try to motivate it. So it's going to require a lot of shortcuts and cheating, but I've already prepared everyone for that. So let me remind you of where we were. Yeah. The basic idea of the whole course really has been around this tower of 2-1 factors. And in there we saw these famous temporary Lieb algebra given by these predictions EI. And then we decided that that was only part of the story, that we should actually start looking at the centralizer tower, M0 prime intersect Mi, and this is finite dimensional. I. The dimension, the asymptotic growth of the dimension of these things is governed by the index of the subfactor. So this gives a lot of combinatorial invariance of the subfactor, and I realized that there is actually one example which one can do completely without any cheating or mucking around. It's sort of trivial. Well, okay, first of all, the most trivial example one can do is when M0 is equal to M1. In this case, the tower doesn't change. The tower is always M1. Nothing changes. Since it's a factor, these relative commutants, these centralizers, are all dimension 1. So that's a really boring example. But you can get a slightly less boring example by assuming that M1 is simply the tensor product of M0 with the k by k matrices. Okay? So then if you analyze this basic construction, this tower, it is quite easy to do, and you find that each step of this you're just tensoring on by the k by k matrices. It's sort of intimidation would get you there. So M2 therefore will be M0 tensor mk of c tensor mk of c, and then M3. And so on. So maybe let me do the intimidation argument. Right? The intimidation argument is simply, all right, this first one, M0 contained in M1, simply tensor product by the k by k matrices. The index, as we all saw early on, is k squared. So what happens to this one? Well, this is also index k squared. And this inclusion is essentially trivial, so this one has to be essentially trivial. So this has no choice but to be tensoring on again by the k by k matrices. Okay? Couldn't be anything else. Just think in the world of possible. All right, so having established that, then it's very easy to calculate M0 prime intersect Mi, or M little k, say. This is nothing but, since M0 is a factor, the centralizer of M0 and M1 is just the k by k matrices. Obvious, and so on. So in general, this is just the tensor product from 1 to k. Oops, we've got k by k matrices. We better have something else here. J. Fantastic. So this is a very simple example, and so we know what the planar algebra is. Remember, I said last time that there was this theorem that these things form a planar algebra in general. These form a planar algebra. And just a quick reminder of what a planar algebra is. It is a sequence of vector spaces, and such that with the property that every time you have one of these so-called planar tangles, this idea came from Conway's approach to knot theory. Every time you have a planar tangle like that, so this is just an output disk and some input disks with privileged, each one of which has a privileged interval on it. To resolve the cyclic ambiguity for gluing, then into such a tangle you can put elements, say x1, x2, and x3, and each of these x's belongs to the vector space corresponding to the number of boundary points. So if the planar algebra were Pn, these are the vector spaces. Then since the number of boundary points is even, we divide it by 2. So this here has 4 boundary points. So it corresponds with the things that we put in are in the vector space P2. So x1 is in P2, x2 is also in P2 because we put it in with 4 boundary points, and x3 is in P3 in this case. And then the output, the result of this multilinear map on x1, x2, and x3 will be in okay, so last time I made the meta theorem that a random integer probability almost 1 of being odd, okay? And this is a typical proof. Somewhere we've got 7 points. I got 1 too many points here, right? Or not an even number. So we've got to put another one. And this is 1, 2, 3, 4, 5, 6, 7, 8. So now this is in X4. And someone tell me which vector space this one is in. The output vector is in P4. Because this one has 1, 2, 3, 4, 5, 6, 7, 8 boundary points. So the assertion, therefore, is that there is what I wanted to get at here is that this theorem implies that there is a planar algebra structure where the planar, where the vector spaces are these tensor of the k by k matrices. Well, that's actually easy to see. Suppose that in this example, x1 were in P2. Well, what's P2? P2 is exactly the tensor product of the 2 by 2 matrices, the k by k matrices twice. So a vector in here is a tensor with 4 indices. Tensor with 4 indices. Right? A matrix, a 2 by 2 matrix is a tensor with 2 indices. So tensor twice, so we get a tensor with 4 indices. So we see that the planar algebra structure coming from this would have to associate, if you put in a tensor with 4 indices here, a tensor with 4 indices here, and a tensor with 6 indices there, it's got to give you a tensor with 8 indices here, and it's got to give you a tensor with 8 indices. Well, there's a completely obvious way to do that, and that is you simply contract along these things here. Contract. So you contract the tensor along this one and this one and this one. And the number of indices left is correct around the boundary. So this is just simple contraction of tensors. It's just, it's like the Einstein summation convention, except that you don't even write the indices in. You just write the structure. This notation, some version of it was due to Penrose. Okay. Yeah.
Sorry, I missed the last lecture, perhaps.
This
is a kind of operand?
This is an operand, right. Exactly. These, these pictures, these planar tangles, form an operad, and this operad structure is gluing. If I took another one of these and had the right number of boundary points, I could just glue it in there. So planar algebra is precisely an algebra over this operad. Okay. Is everyone clear on this contraction of tensors? Maybe I'll do one example just to illustrate what's going on here. I said that this particular tangle is supposed to be the multiplication tangle, so let's imagine that we put in an A here and a B here and see what we get out. Well, I'm thinking of this as tensors, and so we've got a I, J, and K, and we're supposed to contract over this. So this is going to be the tensor whose value at I, K is the sum of A, I, J, B, J, K. In Einstein notation, I guess this would be A, I, J, J, K. B, well, it's the same, except you would remove the sum sign, right? Sum A, I, J, B, J, K. Okay, and that you'll observe is just matrix multiplication. See, and if I put more lines in here, I would just get matrix multiplication in the tensor product of a bunch of matrix algebras. So that's a very explicit, very simple planar algebra, but it's an example that I want you to bear in mind. So in fact, I guess now we have 3 examples of planar algebras that we have introduced. One was the planar algebra of Conway tangles, where we just put in bits of knot. We put in a bit of knot here, and a bit of knot here, and a bit of knot here, and we get out a knot with boundary there. And the other one was the Temperley-Lieb planar algebra, where we put not knots, but perhaps better to say the Kaufman planar algebra, where we put pictures like this in the tangles, and we get out such a picture. Now we have a third example, which is the tensors. So hopefully the idea of planar algebra is more or less gotten across. If you know what an operad is, then this is sort of fairly obviously some kind of colored operad, and planar algebra is simply an algebra over that colored operad. All right. Now back to, I said last time that I was cheating a bit about this planar algebra for a subfactor. So I'd just like to very briefly, in a quick interlude, tell you what the true story is without going through the details. There will be one detail and then we'll ignore it again, because it's just convenient to ignore it. So the real story it involves a duality in subfactors, of which we haven't seen really emphasized yet. So you'll remember that we had M0 containing M1, and then M2, and then M3, and we extracted M0 prime into sec Mi. These finite dimensional C-star algebras, semi-simple finite dimensional complex algebras, very simple combinatorial objects from this tower of, infinite dimensional algebras. Well, the point is we could also have started our tower from here, right? We could have said M1, M2, so we could also have extracted M1 prime into sec Mi. I said at some point that there was a graph, a pointed graph, gamma, such that this algebra is the algebra of loops. Loops on gamma, placed at star. Okay, so there's this theorem that this algebra is very easy to describe. There's this thing called the principal graph. It's the algebra of loops based its star on this principal graph. So in this case here, the principal graph is simply two vertices and k edges. And if you want to be explicit, the algebra of loops, this is the base. The algebra of loops of length, this is of length 2i. If you look at the loops of length 2i on this graph, then you'll find that you've got actual matrix units for this algebra, the tensor power of the k. So it's very basis explicit, very explicit example. You can see the principal graph. You can see these algebras as being linear combinations of loops based at this. Well, see, in general, so this means these M1 prime intersect Mi, they are precisely the tower corresponding to this subfactor here. Okay? So therefore there exists another graph, gamma prime, such that it's the algebra of base loops on that. So in general, when you have a subfactor, you have two graphs. You have the principal graph, and this one is called the dual principal graph. So in this example here, the dual principal graph is the same, obviously. Okay, so this is a sort of very self-dual subfactor. In fact, in case the index is less than or equal to 4, remember we ran through all of the possible principal graphs there. They were these Dinkin diagrams, A, D, E, so on. There, it's always gamma prime is equal to gamma. Okay. However, the Hagerup, which I talked about this great discovery of index 5 plus root 13 over 2, the smallest one bigger than 4. There I drew two principal graphs. The star there and this one here. I've got the right number of vertices and things. Well, these are dual. Okay, one of these is gamma, and one of these is gamma prime. So, well, I said there was two Hagerups, subfactors of this index. In fact, there's really only one up to duality. This is the smallest example for which you get a different principal graph for the dual. Okay. So it's actually very easy to get a different principal graph for the thing in its dual, but you have to go up to index 6 for groups. As soon as you have a non-commutative group, you do that Galois theory subfactor that has different principal and dual principal graphs for a non-commutative group. Okay, so the story is simply, in order to handle this duality, the planar algebra structure has to be enriched a bit, and the idea is that we have to have something that's, we have these two kinds of vector spaces, this kind and this kind. And so the planar tangles have to be somehow capable of telling the difference. And the data that you have to add to a planar tangle is a shading. So because everything's even, you can actually shade, checkerboard shade, all of the regions of this planar tangle. And the idea is, and the dollar signs might be in shaded or unshaded regions. So there's two, the shading is part of the data of the tangle, And the idea is if the dollar is in the unshaded region, the element that you put in here is in the original subfactor. If it's in the unshaded region, if it's in the shaded region, it's in the dual thing, okay? The one coming from the dual subfactor. Well, it's still an operand, it's just that the elements have the shading as well, and in order to glue them, it has to match up plus the shading. So for instance, if this dollar sign were here, then this particular thing would give us an element in P4 for the dual subfactor. If it were in the other region, it would just give you an element of P4. Okay, so a slight addition of structure to the operand gives you the actual planar algebra that really needs to be used in order for the theorem to be true. Okay? Yeah.
I mean, obviously you could repeat it again. Does this lead back to this? There are only two graphs?
Right. That's a very, very good point. In fact, you could, let me start a little parenthesis. A very, very acute observation is that you could take M prime intersect MJ, provided I is less than J. Less than or equal to J. So in fact, you should get infinitely many of these principal graphs, but it is a duality. So if you repeat it twice, you get the same one. But let's just say M0 prime intersect MJ is actually somehow canonically isomorphic to M12 prime intersect MJ. So therefore, you only get two principal graphs. J plus 2, thank you. So you actually only get two principal graphs. And Popper has axiomatized this whole structure in which he calls these algebras Mi prime intersect Mj, he calls them a lambda lattice. And they have various axioms. He also needs, part of the structure is where the EIs sit. Okay, so I have axiomatized them as a different way by planar algebras. Popper axiomatizes the subfactors as a sort of, there's a whole network of algebras, finite dimensional algebras, A00 contained in A01 contained in A02, and so on. And this is a one. Oh, is it like this? Well, however these inclusions have to go, that's a lambda lattice, and you need to know where the EIs sit. And with a bunch of axioms, Popper manages to recapture all of the structure of that you can get out of this invariant. This tower with all of the structure is called the standard invariant. And there's also an Okeanou, quite early in the game, gave us a sort of combinatorial axiomatization in terms of paths, in terms of these loops. Since you have this explicit basis of loops on the principal graph, you can give all of the numerical data so that you can get the planar algebra structure. In the simplest example, this tensor planar algebra, we've got it. That's the planar algebra structure, it's the contraction of tensors. If you unwind all of that, you'll find that you get Popper's structure, you get Okeanou's structure, and you get my planar algebra structure in that case in a very simple way. Okay. There's also a tensor category approach, but it's probably best if I just don't say anything about that. All of these approaches are good in different ways. Maybe I'll just say that Popper's approach is fantastic for proving analysis theorems. Occhiano's approach is, in principle, good for explicit computing and things. My approach is somehow structural. Well, we'll see what my approach really is good for. Rest. I have tried very hard to emphasize, to draw all these pictures with nice round circles, and what's going on in my mind is that there's this sort of very cyclic structure to the whole business. The tensor product, there's no sort of preferred, there shouldn't be any kind of preferred direction. The tensor product and the pop-up approach sort of have a privilege this multiplication structure by giving it a certain direction. I've been trying to sort of get away from that prejudice as much as possible. I mean, I'm not saying it's not a good idea, I'm just saying that I'm trying to do something different. Okay, and so I think we move on to the first thing that is, emphasized by this lack of linearity, which is the annular theory. Okay, so in order to proceed, I want to get out of this shaded world. Simply because every time I introduce a concept in the shaded world, it's a bit more complicated. So I'm just going to deal with planar algebras where the shading is irrelevant. You can just forget the shading. Plenty of subfactors for which that's true. And if you prove something with no shading, then it's always just a matter of detail to do the shaded case. So in order to have a chance of finishing this lecture from now on, all of my tangles and so on, I'm just going to simply assume that they're not shaded at all. I'm going to deal with this simpler operand. Okay, from now on, write that up. Unshaded. And this is basically the sheet. If ever you wonder, if there's something that you wonder how it might work in the shaded world, just ask me and I'll tell you. All right, so the next advance is the annular theory. So one has led to this in various ways. In a purely structural way, thinking of this as an operad and things as being algebras over the operad, then it's very natural to consider these annular tangles. So remember that in the operad picture, this tangle is multiplication. Okay, and so this is an operation which has two inputs and one output, and it's quadratic. It's bilinear in these inputs. You also have these tangles with no inputs. Okay. So there's something intermediate between the no input tangles, this is your Templey-Lieb story, no input tangles and two input tangles, and that's one input tangle. Right, so this is tangles that go from some, we just have one input. One of the pins and we get an output. Okay, these are supposed to both have dollar signs. Right. So, this is something that one might have missed. The richness in this, one might have missed without this drawing round circles. One might not have realized just how important this annular structure is. So an example of one of these annular tangles, here's an example. I'm going to switch colors. All of a sudden my string, well, let me make my strings blue. I might go there, 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 and there. Okay, so that's an annular tangle. And on a planar algebra, this would give me an operation going from P2 to P4. By the axioms of planar algebra, I've drawn here a planar tangle, so therefore I have a linear map from P2 to P4. Okay. All right, so now the nice thing about these annular tangles is that they immediately form a category, a very simple category. Form a category. Well, it's really the same, morally the same as that concatenation we did with braids, except that now they're two annuli. So if I want to take one that will go, say, from 2 boundary points to 4 boundary points, and say it does this. Very interesting one. Let me have some more boundary points. 6 boundary points. It does this. Oops. You see, I'm stuck here. This is an interesting point. I'm stuck. So, because I can't get from this one to this one in a planar way. So somehow I've got to modify my construction. So let me use this. There's a planar thing there. And then if I had another one, then I can simply has the right number of boundary points, then I can simply get back, say, to 4 boundary points, some other tangle that might do. You have to be careful to avoid, I think we're already dead if we want them to be planar. Okay, so this is the composition of morphisms, so the objects simply the integers, union 0, and the morphisms. The morphisms are annular tangles. Right? So the composition of this morphism is simply the result that we get from the gluing, from the operad. And that's how you do it. Now, of course, if you're observant, you will realize that you might, when you do glue these tangles, you might encounter closed loops. Right? This one might have come back on itself. And remember that the story is you throw them away and you multiply by the power of delta. So in order to make this a category, you have to do something to incorporate this delta. The most brutal thing to do is just linearize and make everything vector spaces. So there would be a category, the objects would be the same, but the morphisms would be linear combinations of tangles. Almost set theoretic, but this is a factor of delta. I think it came up last time. You could also leave these deltas in, right? Have a big proliferation of circles and make it a category on the nose. Any questions about that? So, given this category of annular tangles, there's one sort of question that may be lurking in the back of your mind. Maybe it isn't, but it will slowly become a theme for the talk. Is what about these boundary points? How sloppy do we have to be about these boundary points? Well, if we want the objects of the annular category to be exactly just n, then we have some freedom with these boundary points. We can move them around. We have to consider them up to isotopy, so on. But we could also make them quite rigid. We could choose once and for all a collection of n points on the circle for each n, and insist that our tangles actually join those points to those points, and we don't move them around at all. So there's a subtle difference there in if you're just completely sloppy with them, then the rotation of 360 degrees might not actually. If you're completely sloppy, then the rotation of 360 degrees should act by the identity. But if you can be much more rigid, so the rotation by 360 degrees will actually act by something. So obviously that's a very, very special tangle, which is equally obviously going to play a big role in the theory, which is the rotation itself, where this will simply rotate. If we have $here and $here, this will rotate by 1. There's this basic cyclic structure, the whole thing, and the sloppiness is the question of whether if you rotate by 360 degrees, this one comes all the way around to here, and this one goes all the way around to there, and so on. You have to be careful drawing it. Does this actually act as the identity? Well, you can sort of choose it. If you want it to, then you can insist that it does, and if not, you don't have to have that. Okay? All right, so now I just want to tell you about the representations of this category. And I'm going to say C-star world. Or I should say von Neumann world, I guess. Von Neumann. Hilbert space. So by that I mean that I'm going to consider vector spaces, but I'm going to insist that all of my vector spaces be Hilbert spaces, finite-dimensional Hilbert spaces. So what is a representation, therefore, of this category? So the category has objects for each integer corresponding to the number of boundary points divided by 2. It has morphisms for each one of these tangles. So therefore, a representation of this category, linear representation, is going to be a vector space V sub n for each n. And that's going to correspond to 2n boundary points. And given Vn and Vm and the tangle, and a morphism going from n to m, i.e. a tangle, there has to be a linear map. And these linear maps have to compose according to the composition of the annular tangles. That's the obvious notion of representation of a category, and you see that this factor delta just goes along for the ride because we're talking about vector spaces, so we don't really have to worry about it. Okay, now in this von Neumann algebra C-star world, I want these things to have inner products. Now, as soon as they have inner products, they're Hilbert spaces. These are finite dimensional vector spaces. Actually, they don't really have to be one-dimensional in general, but first instance, they're going to have inner products, and the interaction is that the adjoint, so adjoint of the tangle is action by mirror tangle. So each one of these tangles has a map from Vn to Vm. Then the adjoint as Hilbert space operators is going to go in the opposite direction, and it's going to be given by the mirror tangle. Well, by the mirror tangle, I mean take a tangle, any tangle, and draw a circle halfway between the inside circle and the outside circle and simply reflect it. Okay, so in particular, this rotation tangle will get mapped onto its inverse by this. The rotation will be acting by unitaries. Okay. And this, one more, perhaps. If you take a tangle like this, then this is self-adjoint. If you reflect this one around, you get the same thing. So this tangle is actually a projection. It's an idempotent up to this factor of delta. If you compose this with itself, you'll pick up this factor of delta. So this is like our Kaufman capital EIs. It's an idempotent. So EI squared delta EI. We call this EI. So in fact, we have slightly enhanced this Kaufman calculus in that, this now we have a cyclic set of these EIs, so it goes all the way around the circle, whereas before we just had a linear array of them. Right, so what I want to say about these annular tangles and the representations of this annular category is that it's a semi-simple structure. Reps of annular category, and I'll say they're unitary representations, and that simply means that what I said up there, that we're in the C-star Hilbert space world. That means that we have a positive definite inner products on all the vector spaces, and the tangles, the adjoint of the tangle is the mirror. If that's true, then you can, any representation, any pi, is equal to the direct sum of irreducibles. Now this direct sum may actually be infinite, possibly infinite. Okay. And we'll see that. You may wonder, if it's an infinite direct sum, then how can the individual vector spaces be finite dimensional? We have an infinite direct sum. Well, you'll see what happens. When I tell you what the irreducibles are, you'll see immediately what is true. So in order to do this, we have to classify the irreducibles. And here's this classification, which is due both to myself and, in some sense, to Graham and Lehrer. So I sort of started this work and introduced the idea and got a few results. I was stuck on one point. Graham and Lehrer generalized the whole thing to a purely algebraic situation, non-semi-simple and so on. But they sort of solved it in a general non-unitary context. And then I came back and I never could understand their paper, but just looking at it forced me to get over the difficulty that I had. And I got this following classification in the unitary case. So the central idea is the concept of a lowest weight representation. So let me just put it aside. I'll just state it as an abstract structure for the irreducible representations, and we'll see the consequences afterwards. So Vn, so we have an arbitrary representation, and it has the following properties. You find that Vn has to be 0 for n less than or equal to p. That's the main thing. And Vn, for strictly less than p, and Vn is just one-dimensional for n equals p, and that's it. Since it's irreducible, all of the higher v's, so let's write this, Vm equals linear span. So if we have, we can call that some kind of privileged vector, unit vector here, C omega, of tangles applied to omega. And finally, one last parameter. So there's two parameters in these representations. One is what's called the lowest weight, the smallest p, the smallest p for which this vector space is non-zero, smallest n for which this vector space is non-zero, and then it's dimension 1. And then there's this other parameter which is a root of unity, a p root of unity. And that's given by the following. Since this vector space Vp has dimension 1, then if we take this omega and we put it in here and then we rotate by 1, so here we have dollar and dollar. Then this has to be, since it's dimension 1, this has to be another vector in the space. And since this is periodic, this is, well, actually, it's not it's actually an arbitrary number of modules 1. Okay, so I want it to be a piece root of unity, so let me just assume that the rotation, angular category unitary, and rotation, 360-degree rotation equals 1. And this is equal to omega capital. Okay, so that's the whole story for these irreducible representations of this annular category. There's a vector space, there's a unique p, smallest p, for which, smallest n for which this Vn is non-zero. It has dimension 1, and the whole vector space is linear span of tangles, and there's a rotation. This omega has to be an eigenvector for the rotation parameter. So these two parameters, omega and p, completely classify all of these annular representations.
So is delta fixed?
Sorry, yeah, delta is fixed. Now there's I've been doing some cheating about delta. Delta is fixed. And we remember there's two regimes for delta. Delta equals, delta less than 2, and delta equals 2. Actually, it turns out that in this annular world, there's 3 regimes. Delta equals 2 is slightly different from delta bigger than 2. So, and the story about these representations is that if delta is bigger than 2, there's absolutely no restriction on these. P can be arbitrary, omega can be arbitrary. If delta is less than 2, then there's some restrictions, because there are. What are these restrictions all about? Well, they're about positivity of the inner product, right? If you start writing down, you can take some inner products and you find that unless you choose things correct, when delta is less than 2, you end up with things with negative inner product with themselves. Just like in our proof of the 4 cosine squared by array. So it's a bit more subtle, subtle existence. This is probably is always true, but the existence can be a bit subtle in the case where delta is less than 2. This was completely analyzed in the paper by Sarah Resnikoff and myself. In this discrete series part. I had already done it in the generic case. It's quite a bit simpler. It's actually a bit non-trivial in this discrete part, because you have to actually construct the Hilbert spaces. You really have to work a bit to construct the inner product. In the generic case, it's just handed down to you from subfactors. You know it exists for various reasons. Are there any questions about that? So that's the annular theory. It's a very beautiful theory, and it allows you. It's the sort of planar algebra way to attack the construction, the existence and non-existence of subfactors of index bigger than 4. You somehow decompose them with respect to the action of this annular tangle. You see, a planar algebra itself is going to be a module over this because, you know, it's going to supply representations. If I have a planar algebra, and this is a perfectly fine planar tangle, I've got the right to put an element of it in. So if you take any planar algebra, you can simply decompose it by, according to this, it's a decomposition into irreducibles, and these give you invariants of the planar algebra. And that led to, with considerable deepening, it led to an attack on the construction and deconstruction, this sort of existence and non-uniqueness of subfactors. It's sort of, it's the competing version to Izumi, so we're in heavy competition with this concept. Unfortunately, it's an amicable competition, and both sides have joined each other at this stage. Yeah.
Can you say one word about why the category is semi-simple? Why does it split?
It's because of the Hilbert space business. You can take orthogonal complements, and they.
Sure.
It's just like in finite groups. So now you can see why there could be infinitely many irreducibles, because, you know, if they just start, if their lowest weight spaces are higher and higher, then, you know, then the actual individual spaces can be finite dimensional, but they can involve infinitely many of these modules. Okay, so that's a sort of nice theory. And it inspired, it has inspired me from the earliest days to go in this direction which I'm about to go in, and will lead us to representations of Thompson's group and knots and links in a different way. So just before I take the break, let me say just a couple of words about the reason for going in the next direction.
So I still don't have an intuition why this is related to quantum. I'm sorry, this is a professional question.
Why it's related to
Quantum double.
quantum double. Right, well, yeah, that was a shock for me too, I must admit. So, as I said, I developed the theory for the motivations that I pretty much described. But then, at the end of the day, I started telling Kevin Walker about it, and he told me that these annular representations, at least in the rigid case, where you don't insist that the 360 degrees is equal to 1, he said that should be the same as the representation theory of the quantum double. The quantum double is something to do with half braidings, and it's a construction due to Drinfeld. So that was a bit of a shock. I didn't. And one of the predictions was that these things, therefore, there should be a tensor product structure on these irreducible representations. Nothing in here suggests a tensor product structure. But in finite depth, at least, it is possible to give that tensor product structure, and it all works. And so I think it's reasonably well understood now why that should be the case in the work of Corey Jones and Samendra Ghosh and so on.
I should read that.
Yeah, probably. I can't say a magic word that does it. In the infinite depth case, of course, there's really not, the situation is still evolving. what do you mean by the quantum double in that case? Well, there's candidates, and some choice of candidates should line up with this theory. This theory is perfectly fine in the infinite. But there's subtleties about boundedness and so on. Strongly related, I suspect, to what I'm about to say. Right, so anyway, just this super quick version of algebraic and conformal field theory. So the union of algebraic and conformal field theory says that, according to Siegel, according to Doppler, Haag-Roberts, according to a whole lot of people, says that you should have the following structure. Given a quantum field theory, given a conformal field theory, there should be a Hilbert space associated to the circle. In fact, several of them, but there should be a Hilbert space associated to the circle, and on that, and every time you have an interval of the circle I, there should be a von Neumann algebra A of I on H. A von Neumann algebra. Satisfying certain properties, which I'll tell you. I contained in J implies A of I contained in A of J, and more significantly, I contained in the complement of I of J implies that A of I is contained in the commutant of A of J. Okay, so these are two of the axioms, and the idea is simply that this A of I is supposed to be, this circle is supposed to be space-time. It's a one space-time dimensional theory. From conformal field theory, this is supposed to be a chiral half of a two-dimensional theory, if you know what that means. So, but anyway, the point is that to each I, there's an A of I. These are factors. In fact, they're of type 3, but you can think of them as being type 2-1 if you want to. They're not. That's all we really know about, so we'll pretend they're type 2-1. There is this structure, and this means, you see, this means that we have some factor. Because if something is a factor, its commutant is also a factor. So if you take A of I contained in A of J prime, you have a factor contained in a subfactor. And if you make J equal to the complement of I, so we have I here and IC here, then the prediction is that the index of A of IC prime in A of I is, well, finite in rational conformal field theory. This has actually been proved by Wassermann in some cases and extended to lots of other cases by various other people. And the other thing is, the thing that makes it conformal field theory as opposed to just any quantum field theory is that diff S1 is supposed to act projectively, unitarily on H. And it's coherent with these intervals. So if you have a diffeomorphism of the circle, that's going to send these intervals, transport them among themselves, and its unitary representation, if you conjugate by the corresponding unitary, it's got to transport the algebras just as the diffeomorphism transports the intervals. So if we had U alpha of diffeomorphism A of I, U alpha inverse equals A of alpha of I. Okay, so, as I said, this was just super quick. There was no motivation. I just brought this out of midair. Of course, there's a whole many years of theory, but it's the output of a whole lot of theory. It says that conformal field theory should give you this, at least, gives you a lot more. But to every interval on the circle, you get a factor, and in this way you get subfactors, and there's a coherent intertwining action of the diffeomorphism group. Okay? And my idée fixe has been for a long time that maybe you should be able to obtain these Hilbert spaces as limits. You know, in subfactors, we've ultimately come up with this picture that there is a Hilbert space, fine dimensional Hilbert space, associated to the circle with a bunch of boundary points. And the idea is that it should be possible to obtain these Hilbert spaces as sort of continuum limits of these Hilbert spaces. And that's what I'm going to start doing in the next. So let's have a break until 1/4 and a 12-minute break. This is just very simple. This is basically we're talking about this. Yeah, inside this. We're supposed to have Hilbert spaces, and in general, if you have a ring on surface, boundaries. This is supposed to be an operator or form from a tensor product. No, I mean this is sort of the beginning of the field. It even gets started with these Hilbert spaces are constructed there are some signs that it's not work. One of the signs is you know what Thompson did? Piecewise linear, they have problems. Slopes, change, jumps, no jumps. The slopes themselves. Well, it's yeah, right. I'm thinking of this as a sort of discrete there is no anyone big conjugate. There is a conjugacy which smooths things out. Conjugate but unfortunately that kind of thing does not go well with the standard. In sort of so-called West Amino there is sort of functorial, more or less functorial constructions of the Hilbert space. What C would make it. You can do it, but it's really crucial to get at least C2, and this conjugacy just doesn't work. So what I'll do It's a nice count. I'll show that it's as good as the break room. One week's look. Okay. You might want to put it a little bit later because they may need some hints.
Yeah.
So I guess they can, well, they can ask you.
Yeah.
I think you can answer most of them. The other ones are not ones. You know how to turn nonsense, right? You'll learn.
Yeah, I will.
The only one of them is the other one's going to be
Yeah, I can.
Maybe do that Goldman's theorem. Might require a little bit more than what I said.
So, yeah, I'll set your deadline. Yes. Then I'll say that I'll announce that. Okay. You're up. And then July 3rd.
It doesn't have to be text. Maybe the students who can do it. As long as it's quick.
Usually Japanese somewhere.
Some of them they ask very sure. Except to do a break. No, there's one, if you fix delta, at least let's just say in engineering reason delta. If you fix delta, then you have this category. And that category.
来週の月曜まで行って、1週間東北にいるんですけど、また4月1日に帰ってきて、それから10日くらい。はい、質問にはここの3回ですね。ジムに今日教えてもらう。
わかりました。
You still have a question?
多分十分。
聞いていいのかっていうのをちょっと
You still have a question now?
わかりました。質問でまとまらなくてやはり
自分がやったことにそれなり興味を示してくれる。
And for delta less than 2,
違うものができるか
for some and for some people,
新しいとか言ったらそうじゃないみたいな。
so the index is so delta.
これプラナー式の計算をすると、シンプルが分かればいいんだけど、
そうですね。
違う。ビロタイプ。
そうですね。
ハゲラとかでも分かる。
まあいや分かるんです。
計算できる。
なるほどなるほど。
割とかなりいろんなの。蓄税自体。
はい。
exercise in Thompson. It'll be harder for you to Okay, so let's get going. So once again, let me just say a few more words here to get us started on this thing. So, I said according to conformal field theory, algebraic field theory, there should be these correspondences. You should get subfactors by having these algebras. This A of I is supposed to be local observables. And this is the algebra of observables that can be observed completely within this region I. And that gives rise to these subfactors. And what is known is that for some conformal field theories, you do get these subfactors, and you get lots of the ones that we know about. You get the ADE series less than index less than 4. You get lots of quantum groups, you get all kinds of things. But you don't get the high group. By these non-constructions. Now it's also true, things a bit more subtle, that it's obvious that you could never get the high group as it stands from one of these because these automatically have this self-duality. But somehow there's a whole world of subfactors surrounding the high group which has been explored by Grossman, Pinnas Grossman and Noah Snyder, and more complicated examples by Izumi. There's been a whole world of these, and somehow the question is more: can you get into this world by conformal field theory? So in other words, given say the high group, is there a way to construct a conformal field theory such that maybe these ones aren't exactly the high group, but they're somewhere in the high group family? That's the general question. So, and that's my motivation for actually going back and continuing this old idea that I had of getting these Hilbert spaces as limits of the planar algebra spaces. The reason being to try to answer this, because the question of whether the high group actually comes from the conformal field theory is really important, because no conformal field theory so far produces it. So if it does, then we've actually produced new conformal field theories. And Evans and Gannon have some conjecture with some evidence that there is such a conformal field theory. Terry Gannon even claims that he can do it, but every time I ask him, he says, well, it'll just take me another couple of weeks. Oh, just an afternoon of work. So far, he hasn't produced it. So what I'm proposing is in some sense more ambitious, and would be something that would do all of them of any subfactor. But anyway, there's evidence. There's a nice good start, and the start is going to be obtained by sort of using all of this data and trying to get some of it anyway. So one thing here is the diffeomorphism group. We're supposed to end up with a diffeomorphism group. Now, if we're doing this by lattice approximation, we're adding more and more boundary points in the circle. Then we're going to want these points to sort of be, you know, we actually have to put them in somewhere. We're doing physics, it has to be at certain distances. So we're going to have to specify what points we want. And so what we might think will crop up will be, instead of the diffeomorphism group of the circle, in the first instance, we'll get some transformations of these boundary points that we put in, which sort of preserve those boundary points. And this is the reason for thinking of the Thompson group as toy model. So what I am going to produce is Hilbert spaces which carry projective unitary representations of the Thompson group, which have and algebras-a of I, which satisfy everything here except factor. So in some sense, I can complete this program in this toy model, where instead of having a continuum, we have a dense subset of points on the surface. So that's my reason, and the fact that you get an interesting result in that theory is my reason for being encouraged. I've got lots of reasons for being discouraged. In particular, my computer is killing me every day, but continue, things do get better and better. So in order to start this, I have to tell you what the Thompson group is. So since probably most of you haven't seen it before, let me define the Thompson group. There's two Thompson groups, F and S. To define Thompson group F, this is Richard Thompson, not the field medalist guy. His group F, and it's a version for the interval. So the group that I'm really after, of course, is the version of the Thompson group on the circle. But, you know, the Thompson group on the interval will crop up as locally supported diffeomorphism. So in any case, we're going to have to study this group if we want this program to work. So, and it's the easiest, most accessible thing. So here it is. It is, by definition, it's the set of all G, so the G is a map from 0, 1 to 0, 1. And it's a homeomorphism. It preserves 0 and 1. And it's piecewise linear. Okay, so the group of all of those is too big, but we want to make some rather special things about it. So first of all, that it's smooth, so G prime exists. It's the derivative, GDX. It exists for all x not form A over 50 n. So these integers are called the dyadic rationals. Here they are, there's a half, and there's a quarter, 3/4, 1/8, 3/8. So the element of the Thompson group, its slope exists, except possibly at these points. Finitely many. So there's finitely many discontinuities. We have finitely many. Here's another way of saying the same thing. Finitely many jumps in GDX. All at rest. So maybe this is a better way of saying it. Cross that out. Doesn't matter if I say it twice anyway, because the concept has to get across. And the GDX, when it exists, Okay, so these are piecewise linear maps, homeomorphisms from the interval to itself, where the derivative is constant on intervals whose endpoints are dyadic rationals, and the slopes themselves are powers of 2. That's obviously a group, and we're going to examine this a little bit. There's a wonderful reference that you can find, a truly beautiful model of expository notes, which you should read even if you don't, just for that. It's really lovely. It's by Cannon, Floyd, and Parry. And if you do any kind of Google search for that, any subset of that, you will immediately get to these notes. So strongly recommend downloading these notes and reading them just because it's so beautifully done. It's called Notes on Thompson's Proof. I think it ended up being published in L'Enseignement Mathématique. Right, so let's think about this Thompson group, an element. Let me give you a description of an element of the Thompson group. This is how I like to think. This is going to be the way to think of it. So we've got the unit interval, then we want to split it up into subintervals on which each of it'll just be a slope of power of 2. So what we're going to do is we're going to take this interval from 0 to a half, and sorry, if I had that, this wouldn't work. Okay? What I was about to do would not work. We're going to have a slope of 2 in that interval. Well, that would already be subjective. So I'm just going to go as far as a quarter. And I'm going to have a slope of 2 there. So that's going to take that to a half. And then in between here, I'm going to have a slope of 1, so that's just going to translate that into 3/4. And in between here and here, I'm going to scrunch down by a factor of half. So all of the slopes are powers of 2. Here it's 2, here it's 1, here it's 1/2. And this is manifestly a homeomorphism. Everything matches up, and it's smooth everywhere except at these 2 points. Good with puzzle?
So this is not the graph of the map.
No, this is not the graph. A lot of people like to draw the graphs, but I find this about easy. In fact, we're going to have a notation which is even easier. So that's the picture. So you can also think of it, if you like, as a sort of foliation of the unit of the 0, 1 cross 0, 1 by all those lines, where the point here just follows the leaf of the foliation, and it's under the Thompson. This is sort of the most useful way to think about it from the point of view of planar algebras. Okay, so before I want to just spend, so to make you happy with this Thompson group, I want to spend a little bit of time telling you a few facts about it. So it's finitely presented. This is one of the standard generators, and the other generator is you do the identity here and a copy of that in the second half, and that gives you another generator. And there's some 2 relations which are sort of not particularly revealing, but they really express the fact that something happening in here, and the identity there, commutes with something happening there, and the identity there. So rather similar in that spirit to the Gray group. For the more interesting infinite presentations, I'll just skip that. Finally presented, the abelianization is actually quite easy to see. So the quotient by the commutative subgroup, you see, if you take 0 and 1, then there's a little interval around here on which its slope is 2 to the n, and there's a little interval around there on which its slope is 2 to the n. So you get these 2 integers, and the boundary slopes are manifestly homomorphism, so the abelianization is z plus z. Given by these slopes near the boundaries. the commutator subgroup FF is, in general, in group theory, you take the commutator subgroup and the descending central series and so on, but unfortunately this is simple. So this was one of the early examples of an infinite discrete simple group. Commutator subgroup and Thompson group. So it contains no free subgroups. In fact, any subgroup it contains any subgroup that's not cyclic contains an infinite free abelian group. So lots of commuting going on in any subgroup, so it can't contain free subgroup. And the big question about it is this question of whether it's amenable. It was proposed, one of the reasons it was studied so much early on was that it was a potential counterexample. There was this question of von Neumann as to whether every non-amenable group contained a copy of the free groups, and this one was shown to contain no free groups, so it was a hot candidate for being non-amenable with no free subgroups. But no one has been able to prove that it's amenable or non-amenable. It's a thorn in the side of discrete group theorists. From the point of view that we're going to adopt today, it would be extremely unlikely to me that it's amenable. There's only one tiny little bit of reasoning that might suggest that it is amenable. But I don't have a proof. Although I suspect that the ideas that I'm going to talk about will eventually lead to proof. Probably not by me. I have other fish to fry. This is just one step in the quantum field theory program. Any questions about it? Okay. So now I'm going to give you a much more concrete description of the elements of the Thompson group. So in fact, it's going to become one of these wonderful groups that you could actually present right in the beginning of a class of group theory as an example of a concrete multiplication you can get on concrete combinatorial objects. So here it is. The key concept is that it's standard dyadic interval. And that's simply an interval form A is an integer, and N is an integer. So if you have two dyadic endpoints, then the interval is not necessarily of this form. For instance, if you take 1/4 to 3/4, that's not standard. 1/4 and then 3/4. But if you took 0 to 1/4, it is. If you took 1/4 to 1/2, it is. In fact, let's enumerate all of the standard dyadic intervals. So the first one is 0, 1 itself. Then the second one is, if n is equal to 2, there's exactly 2 of them. The first one is 0, 1/2. The second one is 1/2, 1. Okay. And then you keep on going, right? You divide these, you get 0, 1/4. And you get 1/4, 1/2, and you get 1/2, 3/4, and you get 3/4, 1, and so on. So we see that the set of all dyadic intervals has a structure of this tree. All dyadic intervals. All dyadic intervals. Equals planar rooted bifurcated tree. full planar root of bifurcating tree. That's the root, and every time there's a root, there's two edges going down, and each one splits into two. So that's what this collection of standard intervals looks like, standard dyadic intervals. Now there's a little lemma that you can prove, not very hard. It says if G belongs to the Thompson group, if G belongs to the Thompson group, then there exists a partition of 0, 1 into standard dyadic intervals. For I1, I2, Ik, such that, well, this partition is nice for G. So in particular, G is differentiable, G is smooth on each side. And it's one thing. And also, G of Ij is also standard. Okay. So it's just a question of, of making a large enough subdivision until this happens. It's not very hard to prove. You can choose a dyadic. Obviously, you can arrange for the dyadic intervals to be to have constant slope. That's true because it only has these different slopes, so you can subdivide. But it's also, if you subdivide enough, the same is true of the image. So you could subdivide for the interval and subdivide for its inverse, and then you can get a subdivision that's fine. But this has a very interesting consequence in terms of representing elements for the Thompson group, because what is a partition of the interval into standard dyadic intervals? What is a partition of the interval into standard dyadic intervals? Well, it's simply a choice of subtree of this tree. So first, I took this subtree here. I took this subtree, a sort of full subtree of this big tree, because so full means that if it keeps on going, it bifurcates. So if it doesn't bifurcate, it has to stop there. Right, so what's the corresponding partition into dyadic intervals? Well, it's 0, 1/2, 0, 1/4, 1/4, 1/2, and 1/2, 1. So we have a subtree, and by taking the leaves of that tree, you get by definition a partition of the unit interval into standard dyadic intervals, and obviously vice versa. Right? So we can think of, given a Thompson group element, we know that there exists a subtree of this big tree such that the slope is constant on each of these intervals. So remember, I'm thinking of this as being 0, 1/4, this being 1/4, 1/2, and this being 1/2, 1. So by our lemma, there is always going to be a partition. I mean, it might be more complicated on this, such that the slopes are constant on these guys, and the image is a dyadic partition. So if the image is also a dyadic partition in the standard intervals, that's also given by a tree. Right? So we put the tree of that one down here. So we can get this one here. So this pair of trees completely specifies our Thompson group element. Why? Because what's the dyadic partition for this top tree? Well, this is now 0, 1/2, isn't it? And this is 1/2, 3/4. And this is 3/4, 1. So this pair of trees specifies a Thompson group element, which has to take 0 1/4 and send it to 0 1/2, 1/4 1/2 and send it to 1/2 3/4, 1/2 1 and send it to 3/4 1. Well, guess what? That's exactly that one that I just did. That's exactly what this one did. It took 0 1/4, split it to a 1/4, 0 1/4 to a 1/2. It took a 1/4 1/2, took it steady to a 1/2 3/4, and 1/2 1, and then cuts it down to 3/4 1. So this pair of trees gives you a Thompson group element, and from this lemma, every Thompson group element is of this form. Okay? So this is a very nice concrete way to realize Thompson group elements. It's simply a pair of trees, the same number of leaves. So every time, so the moral is every pair of trees same number of leaves gives an element of the Thompson group. Right? Because it tells you which interval to send to which interval, and the scaling factor is then obvious. Okay? Now there's just one little ambiguity which goes on, which is this one. If you happen to have this pair of trees and this pair of trees, then you'll see the thing about it for 10 seconds. This means you can actually clump together these intervals. There's no change. This is 2 intervals on which you've subdivided too much. Okay, so these are called cancelling carrots, if you ever have this. These guys are called cancelling carrots. This is the same thing that in computers, carrots. Type. So if you have cancelling carrots, then you haven't changed the Thompson group. And the theorem is that Thompson group elements are given precisely in bijection with pairs of trees with no cancelling carrots. It's the only ambiguity. So if you have a pair of trees with the same number of leaves, cancel out all the carrots, you've got a unique expression for Thompson group elements. So it's a very, very concrete group given by these pairs of trees. All right. So now, having said that, I want to produce for you the representation, the unitary representation of the Thompson group on the Hilbert space coming from a planar algebra. Okay. That's going to be the game. As I said, it's supposed to be the first step in this program to realize the full field theory. And for me, its very existence is evidence that maybe there's some hope. And in case I never get to say it, there's an obvious circular version of Thompson group that happens on the circle, where it seems to happen on the circle instead of the interval. And this theory extends to that. All right, but let's build it up this way. So I have to define for you a Hilbert space on which this Thompson group is supposed to act. The idea actually comes from this quantum spin change. Because you see, one example of a planar algebra we had was these tensors. So in particular, you can think of the vector space. If you looked at the vector space of a planar algebra for, on the circle with these points, then that really is the tensor product of a whole lot of C2s. That was our calculation. Calculation that we did of the planar algebra for an almost trivial subfactor, tensor product subfactor, was that this is the tensor product of all these C2s is the planar algebra space. And this is what quantum physicists call a quantum spin chain with periodic boundary conditions. This vector space, the power tensors, tensor product of C2s. Quantum computing people also think of this as quantum computing. You know, a lot of mathematical physicists have spent their entire lives studying various operators on this vector space. It's a special case, and the idea is the idea of renormalization, Kadanoff renormalization, is to clump spins into one. And the puzzle that's been puzzling me is, what are you supposed to do if you have more spins? If you all of a sudden you want to put more spins on the lattice, one-dimensional lattice, and you get a higher vector space, and the question is, what's the relationship between them? Well, angular tangles gives you lots of ways, gives you ways of actually embedding one in the other. And the idea is that we're going to choose a matrix R belonging to P2, which has the following property. So if you're thinking in terms of tensors, it's just two tensors with a tensor with four indices, such that if you do this contraction, you get the delta Ij. If this was I and this was J, then when you contract all of these three indices in between R and R star, you get the Kronecker delta function. You want to do it in this concrete example. Right, then the idea is that we're simply going to embed, we're going to take a spin chain with four spins and embed it in a quantum chain with more spins. Then we do it just linearly. Linearly, it's easier to draw, it just makes one thing a bit curious. You're going to have this edge hanging off the bottom here, and you get it. So we've taken the vector space with 1, 2, 3, 4 spins, or P, which is P2, and we've taken that and we're using this annular tangle. We've embedded that into P4. And what do I mean by this? I mean this means so there's a few words about this. What am I doing? If you think of it, this defines a map both ways. You can think of it as a map from P4, the thing with 8 spins, to P2, the thing with 4 spins. And what I've done is I've blocked together these 3 spins and produced a single one by this R matrix. I've blocked together these 3 and produced a single one. So this is what renormalization people in physics would do. Now, in order to, I'm sort of reversing the procedure. I'm wanting to construct the Hilbert space in the limit. So I'm going to go from P2 to P4. Then if I want to add more spins, I will do the following thing. So this now will land me up at P8. If you count the number of boundary points now, there should be 16. So on. Okay? So what this condition simply means is that this is a Hilbert space embedding of this isometry. You'll see if you just do the tensor product, in the product you'll see that this condition is exactly what allows you to collapse the tensor product and you get an isometry. So what we get is P2, taking P4, taking P8, taking P16, and so on. And the Hilbert space is supposed to be the union of those, which you complete. The union of these, according to these embeddings, is obviously a vector space with an inner product, has an inner product because this is an symmetry, and therefore you complete it and you get a Hilbert space H. Okay?
What is R?
R is any choice. All it is, if you're thinking in terms of tensors, you take any tensor with 4 indices, which has this property that when you contract
You
it.
will get very different H's then, no? It's correct. If I change R, I'll get a different H. Of course, it'll be isomorphic because all Hilbert spaces are, but it plays a different role.
But how to about the disk duration?
So maybe I didn't do the relation carefully. Let me redraw it. Well, maybe I'll even write it out explicitly for you. So it's IJK PQ sigma of IJK R, which is also there and there. So Q, J, K, Q, K, J, taking a tensor with 4 indices with this property, and believe me, there's tons of them. There's more than I care to dream about. And every time I have one, as is pointed out, every time I have one, I have these embeddings, these Hilbert spaces one into another. I can take the union. Since these are all isometries, the inner product is well defined on this thing. I can define at any level with the same answer. So I can completely get a Hilbert space. Okay? Clear? So the central idea was this particular plane entangle. And we've never thought of this, I don't think, without having this annular planar algebra structure. I could express this in terms of tensor categories, but this being some intertwined and so on, but why I would ever have thought of doing this, I don't know. So the theorem, if you like, is the first theorem is. Unfortunately, I'm going to have to cut this short because it's only 10 minutes to go to the proof. There exists a unitary representation, let's call it H sub R. We'll emphasize the dependence on H by putting the R matrix explicitly. There exists a unitary representation of F of H sub R on obvious way. And the proof of this theorem is to make the obvious way obvious. So I can do it. I have this beautiful way of doing it, which was suggested by Bill and Thurston, using directed sets and directed systems of nets, basically, and I get a net. The idea is that at the end of the day, you have to be a bit more flexible about. You don't want to double the number of points each time. That can be a bit of a pain. So you allow yourself to embed here and not here in the filter space, and that makes this work very well. But the idea is simply the following: if we have a vector in this Hilbert space. If we have a Thompson group and we want to act on it, okay, then we simply apply the Thompson. We first of all we embed the vector up, which we can do, right, until the scale here is fine enough so that the Thompson group doesn't do anything bad on that scale. Right? It's got to be constant and be smooth on each of these little intervals here. Then we simply use the Thompson group element to spread these out. So we'll do something to these points like that. Okay, but as soon as that Thompson group is not equal to the identity, it's got to do some scrunching, right? It's got to actually squeeze some of these points down. So, for instance, these points might be a distance 1/8 apart. They might end up at 1/16 apart. Which means that unfortunately this vector does not quite land in the space of the right at the right scale. I mean, we're just doing it without doing this directed set when we've got to get back to one of these powers of 2. So in order to get back to one of the powers of 2, we have to embed it, start embedding things up here. Now this one might have a big, this gap might be 1/16 and this gap might be only 1/8. Well, we just fill in things as we have to, and basically the proof of the theorem says that you can do this and it's coherent. You just, if you want to do it in powers of 2, you just follow your nose and it's a real pain in the neck. But if you do it by this directed set argument, then it's so smooth you don't even see what happens. It's sort of good to say it this way. So that's the theorem. So this is my sort of toy model of the diffeomorphism group acting on the Hilbert space. You might object that it's not projective. Well, that's fair enough objection. If you do this, the circle version of the Thompson group, you do get and use analog representations with non-trivial omegas, then you do get projective linear representations of the diffeomorphism. So this actually led me to a question which no one, well, I guess maybe Enriquez claims that he's proved it, which is that if you take the quantum field theory and you restrict to an interval, you have a projective representation of the diffeomorphisms of that interval, from that interval. Then is it genuinely projective? Is it maybe an honest representation? That's obviously not, but to prove it doesn't seem so. Question maybe for a second.
Say it again.
So take conformal field theory, coronal half. You've got diff S1, take the restrict to diffeomorphisms of an interval on the circle. Okay? You get a unitary projective representation of that. Is that honest representation? Every nerve in your body says no, because that's where all of this, these skirmions and things come from. But to actually prove that doesn't seem. Right. So now I'm left with 5 minutes to do the knot theory connection. But, so in order to do that, I just have to tell you what the inner product formula is for two Thompson results. So there's vector psi, or omega, which is simply this vector. So here we're, well, this exists in any planar algebra, so let's just do it. This is a Kaufman tangle. To make it clearer what it means, I should put it in a circle, and there's a string, one string. Right? So what I want to work out is the coefficient g psi xi. I'm given the Thompson group element such as this one here. Well, I just follow the definitions, and so on, I end up with this very simple way of doing it. So what I do is, this is the result of a simple calculation. I take my thing defining the Thompson group, go here, and I add some more strings, and put in, I add some strings, maybe I'll put these in different colors. So the top to the bottom, and in all of these, I put my element R. On the bottom I put R, and on the top I put R star. Okay. This, in terms of tensors, this is just a completely contracted system of tensors. There's some contracted of all the internal limits of sub n number. In planar algebra, it's an element of P0, so okay. Actually, come to think of it, okay, that's it. That's the calculation. You just do it and it comes out. It's just kind of beautiful. That's the way it works out. Now, I'm going to end by switching planar algebras and go to the plane. I'm going to let P now equal C, the Conway. Now, the Conway planar algebra means that all of my elements are little bits of knots with boundary. So the R matrix that I have to define now is not a tensor anymore, it's a tangle. And I'm going to choose this tangle. So what does this picture become? Tell us. the R's have to be replaced by this, and the way the star works is that you just get it upside down. R there and R there. And this one goes there. So all I've done here is I've taken this picture and I've replaced each of these R's by this particular R in the Conway plane. So what do I get? I get a knot. Well, I get a link in general, but then you get a knot. And in this case, a little looking at that thing shows you that that knot is trivial. Well, you might think, well, is it, you know, all of these things are overcrossings on the top, and they're overcrossing, but it looks like you're never going to get any knotting. But the theorem is maybe I'll add an exercise. Actually, I'll add the exercise right now. Theorem, all knots and links. Unorient. So, in fact, the Thompson group is as good at producing links as the braid groups, as all the braid groups. And we saw that you could get those, any link as a closure of a braid. Okay, well, you could also turn that statement into a coefficient. Okay, coefficient. So the analogous statement for the Thompson group is exactly the same thing as for braids. So we see that in this world, you have a choice. You can use a braid group or you can use the Thompson group to get all knots and links. Now so this is the Alexander theorem, isn't it? What remains to be proved, and once again someone should do it, but it probably won't be me, is the Markov theorem. Remember there was the Markov moves which said when two different braid group elements give you the same knot. And I think I know what the moves are, but I haven't really made a serious attempt to prove the theorem. It shouldn't be all that hard, actually. It should be easier than Markov's theorem. So you could, if you want, use the Thompson group to study all knots and links. And it's this theorem that makes me, personally, feel like the Thompson group is not available. So I don't see how you can get all this rich structure, all knots and links, from an amenable group. I mean, the analogous thing with the braid group is the corresponding minimal group is S infinity. So finally, the exercise. Find G1 F. So that's the I G side. Give the triple or not, I have Thompson group. Yeah, and you know, you can, if you want to descend into unitary representations from this, you just apply some jump polynomial. The whole thing, and these coefficients, or the Kaufman scaling theory, these coefficients become numbers, and the number would be the Jones polynomial or other polynomial, or probably group. Okay, so that's it. Hope you enjoyed the conclusion. Getting back into knot theory. Like I never turned the speaker on, so you may not be too much audio there. Is there someone else picking up the audio? So this was not turned on. I'll take it out. the positive definite function on the Thompson group.
Yes, yes, so this is fine.
Put definite yes. Actually, that's an interesting, one of these versions where there's a positive definite function, and the fact that it's actually positive on all elements of the group is equivalent to the four colors. So it could be that amenability, this is one of the lines of thinking that leads to possibly it's amenable. To actually get your Fermat sets or whatever, you have to essentially prove the four colors. So that's, you know this, it's perfectly
So, can we construct the mean invariant of nodes and which is different from the quantum invariant?
well, I mean, there's one that's completely obvious, which is what's the minimum number of leaps? Well, the word of shortest length in the Thompson group, which gives you the length. That's different from any quantum. But if you apply, you can apply the quantum group function and get back to that quantum group. But at this stage, I don't know of any apart from that kind of naive way, I don't know if there's a good way of but, that's a nice invariant. It corresponds to the braid index, right? The number, smallest number of strings in the braid. That's much more calculable because the number of Thompson group elements with a given pair of trees is finite. You count the trees in the bottom, count the trees at the top, work out all of the knots. And if you don't see a knot on that list, then its Thompson index is bigger. So you could just write a computer program right now to figure out the Thompson index. Okay.
大学院生でレポートを提出する人は、それ、It's about format assignment。期限は、7月3日。7月3日ので、数学教室のジムに出してください。で、結構問題難しくて、多分質問せずにレポート書けるとはご本人も思ってないみたいなので、で、ジョーンズさんは、来週の月曜まで、数学教室にいます。で、一旦1週間ほど不在ですけども、その次の水曜日にまた、京都に戻ってで、ご本人に質問するか、あるいは私のところに来れば、すべての問題に対してアドバイスできるかどうかは分かりませんが、ある程度質問には答えられますので、なるべく大学院生の方はせっかくの機会ですからレポートを書いていただきたい。できれば私のところに質問に来て、それで、そうすると多分ヒントとか、どういう論文を見たらいいかとか、そういうことをサジェストできると思いますので。
I hope you said nice thing. I guess I'll be around on Monday also. We'll be in the morning. It's in the afternoon. Right?